See, we'll discuss this problem. Verify the divergence theorem for the function f equals to 4xi minus 2y square j plus z square k taken over the region bounded by x square plus y square equals to 4, z equals to 0 and z equals to 4. We'll discuss this problem. This is a problem on verification of the Gauss divergence theorem. We have to prove over here that for this function the surface integral f dot nds over this closed surface is consisting of the cylinder and these two bases. We have to prove for this cylinder your surface integral is equal to the volume integral of its divergence. First, let us draw this surface. Let's draw this surface. This is cylinder and these are two bases. We will draw this surface. We have drawn this cylinder. Cylinder has got this base. This is z equals to 4. This is z equals to 0. And this is the curved surface. So we have the surface S1. This is S2. And this is S3. Right? So we have to verify this. First, let us calculate this volume integral. Your f is given to you. Your f is 4xi minus 2y square j plus z square k. So your del dot f is going to be 4 minus 4y plus 2z. Del dot f is 4 minus 4y plus 2z. So we have to get the volume integral of del dot f, and this is the region enclosed. We have to get the volume integral over the region which is enclosed by the surface consisting of S1, S2 and S3. So let's calculate the volume integral. Del dot f d tau. I'll use the Cartesian coordinates. So this is 4 minus 4y plus 2z. Let us first integrate it with respect to z. So this is dz dx dy. So the limit of z is from 0 to 4. So this will give you 4z 4yz z square from 0 to 4 dx dy. So this will give you 16 plus, sorry, this is 0 to 4, yes. So 16 plus 16, 32. This will give you this is 32 minus 16y. 32 minus 16y dx dy. So we have integrated with respect to z. And so the triple integral converts to a double integral. What is the domain of this double integral? The domain of this double integral will be the projection of this whole solid on xy plane. See, the domain of this triple integral was the whole volume enclosed by the cylinder, whereas the domain of integration of the double integral will be the projection of this solid over xy plane. And what is that projection? That projection is simply a region which is enclosed by a circle, and the circle is given by x square plus y square equals to 4. So I can say this is 32 dx dy, 16 y dy dx. What is the limit of y? The limit of y will be under root 4 minus x square to 4 minus of 4 minus x square to plus of 4 minus x square. So y dy, y is an odd function. So having the limit of minus a to plus of the type minus to plus a, this will go to 0 from the property of the definite integral, and this will give you 32 dx dy, and that is dx dy integral double integral dx dy is this area. So this will be 4 pi. So it comes to be 128 pi. The volume integral will be 128 pi. Now we have to prove that the surface integral over this closed surface is also equal to 128 pi. We have to prove here that the surface integral is also 128 pi. Let's do that. I'll rub this part. I'll have to calculate now the surface integral of this function over the whole surface. So I'll rub this part and I'll now calculate. I'll remember 128 pi. We have to prove it. The surface integral is also 128 pi. Now the surface integral, the surface over which I have to calculate this integral, consists of three pieces of smooth surfaces, S1, S2 and S3. Now on S1, your n is an outward drawn normal is n will be equals to minus k. N is equal to minus k. So this will give you f dot n is minus z square, and on S1 your z is also 0, so f dot n becomes 0. So integral f dot n ds on S1 comes out to be 0. Now let's calculate the surface integral on S2. On S2 your n is, this n is k, n is k. So your f dot n is going to be z square, and this will be at S2 z is 4, so this will be equal to 16, right? So the surface integral f dot n ds over S2 comes out to be 16 ds over S2. So this comes to be, ds is nothing but area of this base. So this comes out to 4 pi. So this is 64 pi. Alright. Now on S3 is a cylindrical surface. So on cylindrical surface, I told you in earlier lectures how to calculate the surface integral on cylindrical surface. On cylindrical surface, I can take this ds. This ds can be taken as, on S3 your ds is a d theta dz. What is a over here? A over here is 2. A is the radius. So it is 2 d theta dz. And n is, see this S3 is x square plus y square equals to 4. So this comes out to be xi yj upon 2. So f dot n comes out to be 4x square, sorry, this is equal to 4xi minus 2y square plus z square k dot xi yj upon 2. So this will be 2x square minus y cube, 2x square minus y cube. Alright, so now we have to calculate the surface integral. So for cylindrical coordinate, I can take x as, on this surface x is 2 cos theta and y can be taken as 2 sin theta. So this will be 8 cos square theta minus 8 sin cube theta. 8 cos square theta minus 8 sin cube theta. I rub this portion. So on S3, your f dot n ds over S3 is given by 8 cos square theta minus 8 sine cube theta, and ds over here 2 d theta dz, 2 dz d theta. So it is 16 cos square theta sine cube theta dz d theta. Z varies from 0 to 4, so this comes to be 64 cos square theta d theta 0 to 2 pi minus sine cube d theta d theta from 0 to pi. I wrap this portion. So this becomes 0 to 2 pi cos square theta is, this becomes pi, so this becomes 64, this will be pi, and what is this? I'll again remind you, remember this 0 to 2a fx dx is twice of 0 to a fx dx if fx is odd function, so even function, and it is 0 when fx is odd function. So you find this is an odd function. So this is an odd function. Sine cube 2 pi minus theta is minus sine cube theta. So this is 0. So this will be 64 pi. So we get on S1 the total, so the surface integral over the whole closed surface f dot n ds is going to be surface integral over S1, surface integral over S2, and surface integral over S3. So this will be equal to this was equal to 0, this was equal to 64 pi as we have done, and S3 it is again 64 pi. So this is 128 pi. This is 128 pi. So we are here, we are able to prove that your surface integral is equal to the volume integral. We have proved that the f dot nds is equal to del dot f theta. This is f dot nds is equal to del dot f theta. So we have proved this. This is a very important question. All right.